Hello everyone and welcome back. Today we're going to continue our exploration of linear programming and linear programs and talk about the standard form of a linear program. So in the last video we talked about how to do some basic manipulations of, for example, restrictions, constraints, and objective functions for linear programs. So in this video we're going to be working through a variety of different examples on how to convert a linear program into what we say is to be in standard form. So, the first thing that a linear program in standard form must have is that it must be a minimization problem. Also, if it isn't a minimization problem, then there also must not be any intercepts, right? And it can be written in that form C transpose X, where C and X are column vectors. The next thing that must be true is that for our constraint equations, they must all be equalities. There must not be any less than or equal to, and also no greater than or equal to, or no non-equal to statements. Also, all of our variables in both our constraints and our objective function must be presented in the form x is greater than or equal to 0. So though you can't have x2 is less than or equal to 0, you can't have x3 is between -3 and 6, and you can't have any undeclared or unrestricted variables in that expression as well. That means everyone must be accounted for and everyone must be non-negative. If you satisfy all of these requirements for a linear program, then that linear program is said to be in standard form. So let's look at a very basic example. Let's look at the linear program given by the minimization of the functional 5x1 minus 2x2 subject to the following constraints and restrictions. 3x1 plus 5x2 is equal to 6. 4x1 minus 3x2 is equal to minus 4, and x1 is greater than or equal to 0, and x2 is greater than or equal to 0. So question, is this a linear program in standard form? So the first thing that we check is it a minimization problem? Yes, because we want to minimize 5x1 minus 2x2. The next, for our restrictions, are they all x is greater than or equal to 0 form? Yes, both x1 and x2 are both restricted to non-negative numbers, so that is satisfied. Now, in terms of our constraint equations, are they in the form ax is equal to 0? Yes, because we have all equality and we don't have any nonlinear terms in that particular structure. So since all three of these things are satisfied, that means this is in standard form. So the linear program is in standard form. So again, LP stands for linear program. In particular, we can find those vectors and matrices for each of them. So what would our C vector be? So C is going to be the vector associated to our objective function located there. So 5 and -2 are going to be our constants. Then we have our X vector. So our X vector consists of x1 and x2. Our coefficient matrix for our constraints is going to be equal to 3, 5, 4, and -3. And our b vector, which is going to be the constants on the very right-hand side of our constraints, are going to be 6 and -4. And keep in mind, our functional f of x was going to be equal to 5x1 minus 2x2, which of course is in the form ctx. So those are our matrices and vectors for our standard form linear program, right? So that's pretty much the things that we're going to be looking for and trying to convert into throughout the rest of this video. Now let us consider this linear program. Suppose our goal is to maximize the functional 5x1 plus 7x2 minus 8 subject to these two constraints and these restrictions. Is this linear program in standard form? So it definitely is a linear program because pretty much everything is linear. We don't have anything scary going on. So is it in standard form? So usually the very first thing I like to look at is actually the restrictions on our variables. So for our restrictions, are they all in greater than or equal to 0 form? The answer is no, because we have this x1 is restricted to 0 or negative numbers, which is definitely not what we want. So what we do in that particular scenario is we introduce a new variable. Let's call it, for example, n1 n1 prime or x1 prime or something like that. So x1 prime is going to be equal to the opposite of x1, which means everywhere we see x1, we're going to be replacing that with minus x1 prime. Right? Because if x1 is equal to 0, x1 prime also is equal to 0. And if x1 is negative, then that means x1 prime is going to be positive, right? So that's going to switch everything into the positive regime. So once we have that particular transformation, what will that turn into? So it's still going to be a maximization problem, but instead of maximizing 5x1 plus 7x2 minus 8, we're going to be maxing minus 5x1 prime plus 7x2 minus 8, subject to the equations minus 3x1 prime minus 7x2 is equal to 4, minus 5x1 prime plus x2 is equal to minus 1. And then we have the constraints at the bottom. x1 prime is greater than or equal to 0, and x2 is greater than or equal to 0. So now notice that our restrictions on our variables are both positive. Now we can start looking at the other things. So for our constraints, notice that they're all in equal to form, so that definitely does check out. But the next thing that definitely is an issue for standard form is that this is not in minimization form, it is in maximization form. So remember, the minimization and the maximization are going to have the same solution, but the maximum and the minimum versions are going to be reflections about the horizontal axis. So what we can do is we can negate all of the coefficients in that particular term, and that is going to be our minimization functional. So if we convert that to potential standard form, then what we can do is we can minimize the new functional. So what we're going to do is we're going to mirror those coefficients there, and that's going to turn into 5x1 prime minus 7x2. And what I'm actually going to do is I'm actually going to ignore that minus 8 because that's just a vertical shift, and that actually has the same exact solution. And we don't want any intercepts in our standard form anyway, so that's actually going to be closer to what we want in the end. So what is the rest of this going to be equal to? So that's going to be subject to minus 3x1 prime minus, so minus 7x2 is equal to 4, minus 5x1 prime plus x2 is equal to minus 1, with the constraints x1 prime is greater than or equal to 0, and x2 is greater than or equal to 0 for our constraints. So notice it's a minimization problem. There's no intercept. It's all equal to in our constraints, and everything is non-negative in our restrictions. Therefore, this linear program, or we have converted it into standard form. So this linear program is in standard form. And more in particular, you have to understand, even though this is a different linear program, it has the same exact solution as the one we started with. But actually, this is going to be a lot more easier to work with several of the methods that we plan to investigate in this series. For our next linear program, I want you to take a moment and pause this video and look at this linear program and see if you can see if this linear program is in standard form. If it's not in standard form, I want you to tell me what the actual problem is. So after you take a moment and sort of think about it, notice that this is a minimization problem, so that's not an issue. Our objective function looks pretty nice. All our equalities and our constraints are equal to each other, so that's also nice. But notice that we have two variables, x1 and x2, but only one of them is restricted, right? So therefore, the issue here is that x2 is unrestricted, and we can't have that for standard form. So if it is unrestricted, then that means there exist two numbers or two variables, x2 plus and x2 minus, that are both greater than 0, such that x2 can be expressed as x2 plus minus x2 minus. All right, so now we're going to be introducing these two new variables into our equation, and that should fix our unrestricted issue. So what is that going to turn our linear program into? So our minimization problem is not going to change, but the objective function will. So everywhere we see x2, we're going to be replacing it with x2 plus minus x2 minus. So once we distribute that out, that's going to give us 5x2 plus minus 5x2 minus. Make sure you distribute those constants and not forget them, especially if that leading sign was negative. That means that next one would be a plus, not a minus. So for our constraints, that's going to give us 2x1 minus 5x2 plus 5x2 minus is equal to 7. 3x1 plus 4x2 plus minus 4x2 minus is equal to minus 1. And then we have x1 is greater than or equal to 0. We're restricting x2, so we're going to have those two new restrictions added. x2 plus is greater than or equal to 0, and x2 minus is greater than or equal to 0. So notice here that we have two constraints with three unknowns because we've actually represented our old x2 unknown as two new unknowns. So this is still the same exact linear program, except now it is in standard form. And why is it in standard form? Because it's a minimization problem. We have linear, no intercept things there. All our constraints are equal to each other, and we have, for all of our three variables, x1, x2 plus, and x2 minus, they're all restricted to non-negative numbers. Therefore, this is in standard form, as we desire. Now let's consider this linear program that originally has these three variables, x1, x2, and x3. So is this linear program in standard form? So it's a minimization problem. Our objective function looks nice, but notice that for our constraints, which are located in these first three rows, are not all equal to statements. Some of them have greater than or equal to, and some have less than or equal to. Also notice that for our restrictions, x1, 2, 3, they're all non-negative, so actually those aren't the issue, but the issues are located in our constraint section of our linear program. So how are we going to fix that? So notice that if we have a greater than or equal to and we want it to be equal to 4, that means we can subtract some things away from that sum in order to make it equal to 4. So for this particular equation, we need to introduce a surplus variable. Let's call that surplus variable S1. And for this other equation, notice that we have a deficiency because the sum is less than or equal to 10. So we need to add something to that sum in order for it to be equal to 10. So that means we need to introduce a slack variable. And let's actually call that slack variable S2. And keep in mind, once we introduce these, we're going to mandate that S1 and S2 are non-negative. So once we do that, what will our system turn into? So this is still going to be a minimization problem. So it's going to be the minimization of the functional minus 5x1 plus 2x2 minus 4x3. We're introducing our slack variables into our system, so that's actually not going to change our objective function. But what I'm going to do is I'm actually going to put 0s1 plus 0s2 there, just to make my vectorization at the end a little bit more easier to understand. And then, subject to our constraints, so we're going to have x1 plus x2 plus x3, and then we're also going to have plus 0s1 plus 0s2. They're not in the first equation, but technically are. They're with coefficients of 0, and that was equal to 10. And then we have our 3x1 minus 4x2 plus x3 minus 1s1. That didn't get the s2, but I'm just going to put it here just to make things a little bit clearer. And now that's equal to 4, right? So that was our surplus variable introduction. And then we're going to have x1 plus 0x2 plus x3. We didn't have s1, our first surplus variable in there. We're introducing our slack variable into the second equation. That's where our S2 is introduced, and that was equal to 10. And then we have our constraints or our restrictions on x1, x2, x3, s1, and s2 all greater than or equal to 0, right? So that is our new system. Notice that this is a minimization problem. We don't have any constants in our objective function. That's great. We have all equality, and all of our variables are greater than or equal to 0. So once we look at our vectorization versions of this, we're going to have our constant vector c to be equal to minus 5, 2 minus 4, 0, 0. Our x vector is going to contain x1, x2, x3, s1, and s2. Our coefficient matrix A is going to be this 1, 1, 1, 0, 0, 3 minus 4, 1 minus 1, 0, 1, 0, 1, 0, 1. And then our B vector is going to be equal to 10, 4, 10. And that is the vectorized version of this linear program, which now has been put in standard form. Now that we've introduced the basics of converting a linear program into standard form, now let us take this nice little closing example to sort of make sure that we understand all of the concepts associated with the process. So this linear program definitely has several things wrong with it. Let's see if you can maybe pause the video and tell me what you think the problems with it are. So the first thing that definitely is an issue is that this is a maximization problem, not a minimization problem. Second, there's an intercept term in our objective function. We definitely do not want that. The next thing is we have this less than or equal to term, which means that we need to introduce a slack variable. We're going to be calling that slack variable S1. The next issue would be this greater than or equal to symbol, which means we need to introduce a surplus variable into that particular picture. We're going to be calling that variable S2. Also, we have some variables that are not in the right orientation. For example, we have x1 greater than or equal to 0. That's good. But this less than or equal to 0 term, that's not good. So we definitely need to mirror x2 around, call it, say, x2 prime. And we have one other thing. What is it? In particular, we have x4 is not even mentioned here. That is, x4 is unrestricted, right? So that is an unrestricted variable. We need to take care of that. So we have 1, 2, 3, 4, 5, 6 different issues that we need to take care of here. So the first thing I want to take care of is actually our variables at the very bottom, x2 prime, and we need to introduce our variables to restrict the values of x4. So what I'm going to do is I'm going to introduce x2 prime, which is going to be equal to minus x2, implying that x2 is going to be replaced with minus x2 prime everywhere we see x2. And to restrict the values of x4, everywhere we see x4, we're going to write x4 plus and x4 minus, the difference between them, where x4 plus and x4 minus and also x2 prime are all non-negative values. So what is that going to do? And also I'm going to eliminate this constant here because we already know that objective function is also going to be maximized, and once we negate it, also going to be minimized at the same exact x value point. So that's going to give us the following linear program. Let's actually mirror that objective function to turn it into a minimization problem, because that's actually not too bad. So we're going to have 4x1, and then remember when we originally had 2x2 for our maximization problem. That's going to go to minus 2x2 prime for the maximization problem, and then we're going to mirror that, so it's going to be 2x2 prime for the minimization problem. So this is going to give us 2x2 prime plus 3x3, and similar logic is going to apply to our x4 terms, in particular minus 4x4 plus 4x4 minus. Because it used to be plus minus in our original substitution, then when we reflect it, that's going to be minus 4 and plus, and we're deleting our constant term at the end, so we don't need to worry about that. So then we have subject to, so we're going to have x1 plus x3 is equal to 8. We don't need to change anything there. We're mirroring our x2, so that's going to give us minus x2 prime, and then we're decomposing x4 into x4 plus minus x4 minus, and that was originally equal to 12, so we don't need to change that. And then we have x1 minus 3x2 mirrored, and then plus 2x3, but it used to be a less than or equal to symbol on that third constraint, so that means we need to introduce that surplus variable, so that's going to be plus s1 is equal to 37. Introduce the slack variable, pardon my wrong terminology there. And then for our last constraint, we have 5x1 minus 4x4 plus 4x4 minus, and then minus x2, s2, that's going to be our surplus variable because it used to be greater than or equal to 4, and now we want that to be equal to 4, so we need to take away that surplus. And then for our restrictions, we're going to have x1, x2 prime, x3, x4 plus, x4 minus, s1, and s2 all greater than or equal to 0. So once we look at all of these things combined, so we have our objective function, we have our constraints, and we have our restrictions at the end, we ask ourselves, is this in standard form? And the answer is yes. So what are going to be the vectorized representations for each of these terms? So let's start off with the vector x. So x is going to be equal to, we can go in the same exact order, so we have x1, x2 prime, x3, x4 plus, x4 minus, s1, and s2. So we have 1, 2, 3, 4, 5, 6, we have 7 different decision variables there. And then we look at our objective function, and we should have 7 constants there. And indeed we do. Notice that we have 4, 2, 3, minus 4, 4, 0 for S1, and 0 for S2. So 4, 2, 3, minus 4, 4, 0, 1. So we're going to have 4, 2, 3, minus 4, 4, and what do we have else? Yeah, 0, 0. 0, 0, right? So that's again a7 by 1. That would be the same exact dimension. And then we have our coefficient matrix A. So A is going to be rather large. So we're going to have 1, 0, 1, and 1, 2, 3, 4 zeros. And then on the second row, we're going to have 0, minus 1, 0, 1, minus 1, 0, 0. And then we're going to have, let's see what was on that next row. That's going to be 1, minus 3, 2, 0, 0, 1, 0. And then we're going to have 5, 0, 0, minus 4, 4, 0, minus 1. So at least if you look at our original variables, at least without the reflection of x2, what can you tell me about these two columns here? So that's usually going to correspond to your surplus and slack variables most of the time, right? So those are usually only going to consider of ones and negative ones. So what was that 1 there? Well, that 1 corresponded to our slack variable because we needed to add something to it, and that minus 1 corresponds to that surplus variable because we had to take away some things to make it greater than or equal to into equal to. So there's just some conceptual things that you should be able to see from the matrix form. And lastly, our little vector b is going to be equal to 8, 12, 37, and 4, right? So all of those things together will generate our standard form for our linear program. Now, before we say goodbye for the day, I just want to mention another type of linear program that you may, well, it's not really a linear program, but it's sort of linear in the geometrical sense. For example, if you have 5 times the absolute value of x1 plus x2, and let's assume that we're minimizing this subject to, for example, 3x1 plus 2x2 is less than or equal to 5, with the restrictions that x1 and x2 are greater than or equal to 0. Now, at least from the geometrical sense, you should be able to see that, okay, we have x1 being greater than or equal to 0. Therefore, the absolute value of x1 is always greater than or equal to 0. Or the absolute value and x1 are actually always equal to each other. Because if you look at this graph, that's always going to be a v. And we're taking a look at just this region for x1. So that's, of course, always positive. But in case this is not actually given to you, you can actually always rewrite the absolute value in terms of 2 other linear things. And in order to do that, what we can do is we can introduce, again, x1 plus and x1 minus, and we can write this as the minimization of 5 times x1 plus x1 minus, and then we have that plus x2 just sort of hanging out at the end, subject to, we're still going to have our 3x1 plus 2x2 less than or equal to 5, and then we're going to have our x1 and x2 greater than or equal to 0, and we also have these x1 plus and x1 minus terms that we just introduced, also greater than or equal to 0. But in order to take care of the other side of this graph, we also need to introduce a new restraint. In particular, x1 must be equal to x1 plus minus x1 minus. So every time you see an absolute value in your objective function or somewhere else, what you pretty much do is you replace xk equal to xk plus plus xk minus, and then you add the constraints that xk is equal to xk plus minus xk minus, and maybe you want to sort of think about why we need to introduce that constraint once we have that particular transformation of that absolute value term. So those are the basics of converting general linear programs into the standard form, which is definitely going to be very, very beneficial later on down the road. But until then, I hope you take care. See you later.